And welcome everybody to the latest Diamond Anvil, Too Hard to Smash. This one's co-hosted by Eugene the Philosopher. Eugene the Philosopher Bagashov. And today we're going to be talking about condensed matter. What is it? What if celestial bodies were made of it? A little bit about the current theories and stuff. Sort of what goes into lattice structures and all sorts of things like that. Welcome, Eugene, to this fireside edition.
Yeah, hello Daniel. Hello everyone else listening to this and watching maybe even.
Indeed, indeed. So let's first start things out with talking about the Diamond Anvil. This is a sort of an ongoing series on the channel, and we haven't done an episode for a while. And indeed, I made the Diamond Anvil and called it. I authored the name Diamond Anvil, and I called it what I did because of the sort of cutting edge aspects of diamond anvils. So, diamond anvils are important nowadays because of condensed matter physics, which is, I guess you could say, it's a fifth state of matter. I mean, Eugene, what do you say about that? Most people will tell you there's four states of matter. Condensed matter, I think, is probably a legitimate fifth state, and it's really in its infancy.
Well, there are discussions about what you really can call a state of matter. I mean, some people say that, let's say, hypothetical quark gluon plasma might be another state of matter. Some people say that, liquid crystals may be considered another form of matter, etc. So it's all, conventionalized. It's all based on basically what people agree to call it.
Sure. I can appreciate
there are many possibilities here. So in some sense, yeah, you might say that, let's say, the states where you have extremely high pressures and possibly temperatures as well, they behave completely differently with respect to, let's say, the regular solids or something. So, and not only solids, but anything else, because when we're talking about diamond anvils and stuff like that, you also have to understand the transient character of the phenomena we have there, because, well, obviously you cannot support such a process for a long time. So there's also difference in this respect. That's what I'm saying.
Sure.
I mean, if you use the thing, it happens very quickly, right? So it's like a tiny fraction of a second when you have this pressure, let's say.
Right, and so to transition here, space is sort of a weird place, right? It's very difficult to have good insight into what's going on out there, and there's been a number of papers recently coming out suggesting that the smaller gas giants like Neptune and Uranus actually have, and I'm obviously showing Saturn and Jupiter here, but Neptune and Uranus perhaps have condensed matter water at their cores, or somewhere in between their atmospheres and their cores, right?
Yeah, it's actually they are sometimes called ice giants or icy giants.
Right. Ice giants. Yeah.
Or something like that. Yeah, whereas Saturn and Jupiter are considered to be true, so to speak, gas giants.
Yeah, and I would say it's pretty plausible, to have condensed matter. And typically, the pressures that we're talking about here are like 1,000,000 atmospheres to get to liquid metallic hydrogen, and I think it's even higher than that to get to the what they call super ionized water states. And they're interesting because they fit a lot of the characteristics that a planet would have to have a magnetosphere, I think. So, what do you have to say about that?
Well, I would say that we don't know how magnetospheres appear in the first place, what generates them, etc. So a lot of things are possible. But if you're talking about like super high pressures, for example, then, well, we have examples of bodies with magnetospheres which are not very big, I would say. Let's say Mercury or Ganymede.
Uh-huh.
They're, well, roughly speaking, much smaller than Earth even. So I'm not so sure that you need some super complicated process, or rather some super exotic form of matter to get a magnetosphere. Uh, I mean, that's my personal opinion. I mean, of course, it may be possible that it is the case, but I think some simple, roughly speaking, process should produce the magnetic field that we observe on Earth, let's say. We just don't know the process, and we don't know the internal structure of the Earth either. So,
Right, exactly. And this is part of the reason why this is my desktop. So I spend a lot of time looking at this, thinking about this. The first time I took an earth science class was in like 1987. Um, but I started thinking about things like cosmic rays back in like 1981. And so I'm very interested in sort of how these things actually work, right? And I guess what this cutaway is drawing. You can see that, right, Eugene?
yeah.
So what this cutaway is showing, it's basically showing you the Earth's mantle. I mean, the crust is a very, very tiny, tiny layer on the outside of that, and then of course the hydrosphere and the atmosphere um, on the outside there, and then it's showing you. I would imagine based on the size of that, it's probably showing you the outer core, and just a little bit maybe for the viewers about the what you'd call the conventional model of the Earth is that it has some sort of an iron dynamo inside of it. The core is believed to be made of iron and nickel, and then you've got this sort of liquid portion and this solid portion that acts kind of like brushes in a motor, I suppose you could say. And that's sort of the theory on how Earth's magnetic field is generated. And I think Eugene would probably agree that there are some issues with that sort of theory that it's just liquid iron sloshing around down there.
Yeah, well, it's actually some people mistakenly assume that the Earth's magnetic field is kind of like ferromagnetic type of field. So it's that the inner core itself is magnetized like a permanent magnet or something like that. Whereas, I mean, it's not what the accepted quote unquote theory states. I mean, the argument against this made by these people is that, well, it's too hot for a permanent magnet to exist, which is correct. But I mean, we don't really know how hot it is there, but probably
Exactly.
pretty hot. But anyway,
Probably.
so the real, so to speak, mechanism that the current theory proposes is that indeed it's this series, like a complicated system of flows of various metals. Yeah, and I think, yeah, probably iron, maybe nickel, and maybe even something like potassium. I'm not really sure. Like, I'm pretty sure that the experiments that have been done with dynamos involved potassium, but I'm not really versed in all of that, so I cannot tell why or any of that stuff. But
Sure,
yeah,
sure.
basically, we're talking about the system of flows of basically ions of these metals. So it's an electric current fundamentally, and it produces the magnetic field. And it is assumed that these flows, just like any fluid dynamics, are inherently chaotic, and that's what causes magnetic field reversals. So some vague, I don't know, chaotic process somehow leads to all this nonlinear dynamics where you have basically your field like splits in two and in four, and then kind of reverses itself.
Sure, and there are most certainly irregularities also, and you can kind of see it. This is just an artist rendition here, obviously, but you can see these irregularities, and it's quite likely that whatever that inner core is made out of some kind of a metal, like you've said, because of various different. A million papers are written about this. Uh, about the fact that there are these irregularities in the Earth's magnetic field, and they can be measured seismically, I believe it is. And yeah, so The real question is that really what's going on inside the Earth? So let's just
Yeah. That's what I wanted to say myself. That it is all that I've said is based on, again, in air quotes, accepted theory of the Earth's interior, which I not necessarily agree with. Like I think it has way too many um, like internal contradictions and problems. Like again, I've said many times that you need mantle to be, let's say, liquid in order to support, all these convective flows, aka plate tectonics motion. But at the same time, you need it to be solid to transfers to be able to transport S waves, shear waves, from seismic events. So it's internally contradictory. But of course, again, you might argue that, well, it's not solid and not liquid. It's something like other, just as we talked about
right.
other like states of matter. But who knows really? Like and again, even our judgment about the depth, let's say, of earthquakes is currently heavily model dependent. So we don't really know if it happened like really 600 kilometers or 400 kilometers below, or it may happen, I don't know, 100 kilometers below. I'm just mentioning this to kind of emphasize, I guess, the point that it seems, according to accepted theory, that earthquakes may happen at least as deep as 660, I think, was the deepest one that we detected. So, and below that, who knows? Maybe it's hollow. I mean, really.
I've heard the theory. So what you're saying is, uh, when we see a deep earthquake, the depth of the earthquake is not entirely based upon the triangulation of different seismometers around the world because they're not detecting it from far enough
Uh,
away.
what I'm saying is you have to initially assume how a seismic wave would propagate through your medium. You see, we don't have any evidence, I mean, any actual observations about the medium itself, like
Right.
what the mantle looks like. So we don't really know how a seismic signal would be traversing it. So we
Right.
have
Right.
to assume all of that. And that's why I'm saying that it is inherently model dependent, how we judge the depth.
Right. A seismic signal
Right.
is going to
So, I mean, just
propagate.
just roughly speaking, if you detect an earthquake right below you, you may assume a very high speed of propagation, and then you would assume that it may have been deep. Or you may assume a lower velocity, and you would conclude from that that it was not very deep, right? So that's what I'm saying. And inherently, we have no way of knowing.
Oh, is that the way it works? So if it's a if it's a very slow propagating earthquake, it'll be detected as a deep one.
Well, I mean, just taking, distance divided by velocity, you get the time, so something like that. Um, that's what
Yeah,
I'm
I,
saying.
I should probably look into that more. Actually, the way that that's model dependent, because yeah, you're definitely right. Because the planet's too big, and the earthquakes are not detectable from far enough away to be able to just use the triangulation of seismometers, right?
Yeah, what I'm saying essentially is you can triangulate on the surface to get the location of the epicenter. Um,
Yeah, but
epicenter is the projection of the actual focus of the earthquake onto the surface of Earth,
yeah,
right?
but we're
So
just
you
talking
can
about the
easily
depth.
triangulate. You can easily triangulate the epicenter, but you have no idea how deep it was unless you have a model of, how exactly the signal is propagating.
I see. All right. So anyway, now I've got another slide on the screen here, and this is just a current animation of the Earth's magnetosphere. And now this is heavily model dependent. Also, this is the space weather modeling framework, and you can read about that if you like. It's down here in details for the viewers. Just geospace magnetosphere movies, and we're just showing this as a visual. And you've got sort of the parameters of the magnetosphere here. You've got these two plasma spheres. The one on the back is a little smaller, And then you've got these Van Allen belts, and it's not cooperating. Come on now, you can do it. Anyway, those plasma spheres are sort of suspended by the Van Allen belts, which is sort of the electrons that surround the planet. And this is what we're talking about when we're saying, hey, where did those come from? And obviously one of the theories is that they're coming out of the sun and they're getting trapped there and staying there. And Eugene, any input on this?
Yeah, I just wanted to say that firstly, it's not only electrons, it's protons too. But secondly, I don't think we're talking about Van Allen belts in this particular picture because it talks about pressure. And Van Allen belts are belts of high energy protons and electrons.
No.
Like
I'm just saying that this elicits where they
mega
are.
electron volts energies, which is not a regular solar wind. It's actually much more energetic than a regular solar wind. Whereas here we're seeing like the bulk of solar plasma, which is relatively slow if we're comparing it to the velocities of particles in Van Allen belts. So I don't think it's the belts. That's what I'm saying.
No, I'm not saying it is the belts, but you can see where they are because, for instance, this area, this empty looking spot right here, that's the plasmasphere. There's the other plasmasphere, and the Van Allen belts are going to be surrounding that plasmasphere. That's what keeps it suspended in that spot. That's all I'm saying. So anyway, yeah. So let's move on to the next slide here. Any other? We're going to eventually tie things together, folks. So don't worry. Anything else about the magnetosphere, Eugene?
Yeah, I just wanted to repeat what I've said. My recommendation to read Alphin's Cosmic Plasma because he describes there again this alternative approach to the description of the magnetosphere. Like in regular, let's say mainstream, again in air quotes, magnetospheric physics, I guess you would describe it as a bunch of field lines, magnetic field lines, which are like bended and twisted and whatever. Whereas you can apply an alternative approach where you would describe it as a system of currents, let's say, because again, currents and magnetic fields are interchangeable essentially. So unless we don't know what produces the certain magnetic field, then yeah, it's better to talk about the magnetic field. Like again, I've said, we don't know how the solar magnetic field is produced, so let's just talk about the magnetic field. I mean, we don't know the system of currents that produces it, so we cannot really apply this approach. So we talk about the magnetic fields. But in Earth's case, we can actually measure what's going on, and we can deduce the system of currents that produces the picture that we observe, this particular one. Like when people say about, people talk about bow shock, for example, where again the supersonic solar wind kind of slams, again in mainstream terms, into the Earth's magnetosphere. You can also talk about current sheet because bow shock is a current sheet. So, and that's why, I mean, all these magnetic field lines get deflected as they are because there's this sheet of current that produces this perturbation. So basically what I'm saying is there is an alternative approach to all of this. And in some situations, like when you describe magnetic substorms, again, the famous magnetic reconnection mechanism, etc., you can actually, talking about currents is much more effective because it shows you how exactly the particles are getting accelerated, i.e. by the currents, and how the energy dissipates in the system, etc. Whereas, again, in terms of magnetic fields, you can only wave hands around and talk about magical snapping of magnetic field lines. That's what I would say.
Yeah, and
and again, it's not my idea. It's what Alfin talked about in 1970s.
Oh, I get the way that you can interchange electric current. I mean, you've got a current coming out of the field, and you've got a field coming out of the current, and you've got a current. That's literally what a Lichtenberg pattern is, and so on. But this is all based on the space weather modeling framework, Eugene. So this actually does this includes all of the measurement of where the relativistic electrons are and all that stuff. It's quite a complicated model, and the reason that we watch this one instead of the older one on the integrated space weather analysis page is because this one doesn't have the sloppy numbers where you can have negative numbers for certain fields and stuff. Things that can't possibly happen that are happening, that it's showing happening in the magnetotail and so on. So anyway, let's.
But this particular graph only shows you the dynamic pressure in the plasma. It doesn't really show anything else. So basically,
there are actually three.
How much stuff there is multiplied by how fast it's going. That's what we're seeing here.
Yeah, that page shows you three different panes. It shows you the density, the velocity, and the pressure, which is, you could sort of say it's a product of the two, I suppose.
Yeah, exactly. I think it's proportional to the velocity squared and to the density. So yeah.
Yeah. So anyway,
I think so, at least.
So one of the things that we wonder about is where do all the electrons come from, and this is one of the sort of the great questions. If you wanna get a very evasive answer, ask a NASA scientist why sunspots are dark, and if you wanna really confound mostly anybody, you can ask them where all the electrons come from. And so what I'm showing here, this is actually a diamond anvil, and this is a very small thing, and they're just literally pressing these diamonds together, and in between these, there's a little slot that goes, in between each of these, where they're placing some hydrogen. And to measure what's going on in here, they have to shine a laser beam through here, and they have a collector on the other side, obviously. And what they've noticed is that when they put hydrogen in here, the hydrogen turns black and becomes superconductive and forms into a lattice structure. It starts to look like graphite, and it has completely different features in that it forms into this lattice structure where electrons are just free to flow around on it like a metal. And it requires about 1 million atmospheres to accomplish that. Any thoughts, Eugene?
I'm not sure about this claim that they've observed the lattice. I'm pretty sure that the metallic hydrogen was produced, but I'm not really well versed in its properties. So I cannot confirm this.
It did indeed turn soot black. I'm not sure if they physically observed the lattice structure or not, but one of the more vague arguments for the idea that stars are made of liquid metallic hydrogen is that there's a lot of hydrogen in the universe. As far as gas that's floating around, and even cosmic rays, the solar wind, and practically everything out there that we see, all the stuff that sort of isn't stars or planets. And what we see all kinds of molecular clouds. We see giant clouds of water. We see giant clouds of carbon monoxide and all kinds of different chemicals out there. But for some reason, there's an exceedingly large amount of hydrogen, including coming out of galactic scale jets and so on. And so I think this is sort of a reason to study hydrogen a little bit more. And I'm trying to segue here into robotized paper. Any brilliant ideas, Eugene?
Well, you just say, let's examine robotized model.
So I'm not exactly sure how he came up with this idea. For those of you not familiar with,
I can vaguely tell you the story, which is very simple. He basically worked on MRI.
Okay, that was my guess, actually.
And what? Excuse me?
I said that was my guess, actually, that he somehow figured it out because of MRI
basically, long story short, he figured out that not all radiation is black body radiation, and then the question have arisen, like, what produces black body radiation? What exactly you need to have a black body radiation? And from that, you can quickly understand that, hey, if the sun, well, I mean, his kind of a corollary, I guess, conclusion was that you need a lattice basically to produce black body radiation, and then if you realize that the sun has black body spectrum, it means the sun is also should have a lattice, and it's not a gas. That's the line of reasoning, basically, as far as I can tell.
Okay, and for the viewers, if you're not familiar with Pierre-Marie Robitaille, he is a radiologist from Ohio State University. He's from Canada.
I think he no longer works there, actually. Like maybe a year ago, he sent me an email that I don't know if he resigned himself or he was fired or something. I don't know.
Oh.
But I don't think he works there anymore.
Oh, interesting. I wonder what he's doing.
Well, makes Sky Scholar videos.
Anyway, after Robitaille wrote this paper, it didn't get a lot of traction, but he spent like $300,000 out of pocket to publish a full page advertisement in the New York Times.
It was actually before this paper, I think.
Was it before the paper?
Yeah,
No, I think it was 14 or 15. This is 13.
No. I think it was earlier, like maybe even early 2000s, but I'm not sure.
Oh, was it that? Oh.
I mean the newspaper.
Well, in any case, the guy's got some convictions about it. If you haven't read 40 Lines of Evidence for Condensed Matter, the Sun on Trial, Liquid Metallic Hydrogen as a Solar Building Block, it's highly recommended. And it's, I don't know about you, but to me, it's by far the most plausible theory of how a star works, I guess you could say. What a star is. The internal structure of the star.
Yeah. Yeah, I mean, the paper is kind of overwhelming.
Yeah.
Not all the arguments are very strong, but taken together, they look very impressive.
Yeah. And so, part of what Eugene was talking about there is that you need a structure such as what's on the screen now, this lattice structure. And one example of a material that has this lattice structure would be graphite. And, people have been coating the insides of boxes and messing with black body radiation since the 1800s. And this structure behaves like a metal. And again, we don't have a lot of liquid metallic hydrogen to mess with because it has to be under such massive pressure in order to create it. But apparently, when you put water under enough pressure, it forms into a similar substance. In fact, the liquid hydrogen rolls around inside of the oxygen lattice, which forms sort of in a similar fashion to this. So this raises even more questions now as to what happens if you have other chemicals in there? Which one decides to form into a lattice? It's very interesting branch of science, and it's more of the reason why plasma isn't magic. Also, if you expose a structure like this to other molecules, it's going to have a tendency to want to give up electrons. Correct, Eugene?
I don't really get it. If you expose it to what? To other chemicals?
If you expose this to other chemicals, it's going to want to perform chemical reactions because electrons flow freely around this lattice. If this was liquid metallic hydrogen...
Well, you see, there are different types of reactions. In one reaction, something gives electrons. In the others, it receives electrons. Well, that's kind of a really simplified version of chemistry.
Yeah.
But, I mean, to have a covalent bond, is it called in English?
Yeah, covalent bond, yeah.
Yeah, so it's basically an exchange of electrons. Of course, we also have other types of chemical bonding, maybe not entirely chemical, not all of them, like ionic and metallic.
Sure. And you've got exothermic and endothermic reactions and so on. But in order for the sun to produce a white light emission spectra that it does, we don't know of anything else in the universe that produces it besides some sort of a vibrational lattice structure. And that's what Robitaille is talking about. That's one of the easier ways to explain to somebody uh, the 40 lines of condensed matter theory. And again,
I have to make sort of a caveat here, or comment perhaps,
by all means,
that basically what Robitaille does, like one of the main things he considers is Kirchhoff's law of thermal emission.
yeah,
Where it's like middle of the 19th century, but he derives what would happen, the basic law of emission, that if you have basically that states that there are certain bodies that emit certain type of radiation, let's put it that way, which is a black body radiation. And Robitaille examines his claims step by step and shows that it's not applicable to many real bodies. So real bodies would emit something else. It's along the same line of reasoning of Robitaille's, of what exactly emits this specific type of radiation, right? So he basically demolishes the claim of Kirchhoff that all the bodies should emit something like that. So he asks, well, what specific bodies should emit like that? But anyway, currently, and Planck's famous equation for this black body curve, it is based upon Kirchhoff's law, right? So basically, Robitaille's claim is that, well, if Kirchhoff is wrong, then Planck's curve also cannot be applied to all the bodies. This is the reasoning. So, but what I should note here is that currently we don't arrive at Planck's curve from Kirchhoff. Like currently we have quantum field theory, and in quantum field theory you can show that if one condition is met, then you would arrive at Planck's curve. And this condition is that photons can be created freely and can be absorbed freely, photons of any wavelength. So if you have such a system that allows any frequency, any wavelength photon to be absorbed or emitted, then you arrive at Planck's curve for absorption and emission. So yeah, and it's considered to be like, the default state of electromagnetic field in the first place. But that's a sort of a tangent. So the question still remains. It's not really denying Robitaille's argument, because the question still holds: what kind of system can allow any wavelength photon to be emitted or absorbed, right? So the question kind of still remains. But modern theoretical physics considers electromagnetic field itself as being able to generate and destroy any sort of photon. So it's still kind of a narrow spot, I would say, of this theory. But it doesn't, in my opinion, invalidate Robitaille's claims. But let's say it makes them a little bit doubtful, but it doesn't invalidate them completely.
Oh, and by the way, if you see a Peratt instability in the sky, viewers, or if you see synchrotron radiation, and if you see those things in the sky, please make sure you head to a synchrotron radiation
shelter.
Yeah, a synchrotron radiation shelter.
It reminds me of this joke about, you can only look at the sun in the telescope twice. So it kind of reminds me, like you can only see a synchrotron radiation twice.
Yeah. If you see a nuclear weapon go off, make sure you cover your eyes.
Yeah. But if you see it, I mean, it's kind of too late already.
So by the way, this is sort of Robitaille's. This is Robitaille's explanation of a coronal hole. Essentially, what happens is when a coronal hole happens, the reason it's blasting out protons is because when these lattice layers break apart, the hydrogen starts to come flying out of here because there's pressure in these intercalate layers because of the gravity of the sun.
Yeah, I think it's more like they don't really break, but they kind of turn, if you know what I mean. Like on the equator, they are parallel to the surface, whereas in coronal holes, let's say at the poles, they are more like vertical.
Yeah, so. Exactly. And for some reason, I mean that might be like a reduction in the sun's mass going on at the same time, but ultimately we really don't know because we have no idea what the heck is going on at the poles. So I just wanted to show this slide here, just to sort of show the lattice. I think that's a pretty good visual, right? You know, you can see the lattice from the side here, and then in between there you should have a layer and then some intercalate gases and then another lattice layer and so on. And this sort of explains a little bit about what's going on in terms of the activity on the sun's surface.
Yeah, and it's his explanation for processes like CMEs and again novae, supernovae, and just novae. It's when these intercalate layers explode essentially. So the lattice layers themselves get expelled, and that's where you get CME, for example.
Right. Yeah. Exactly. And you know, if they're made of hydrogen, it explains why the solar wind is almost entirely made of hydrogen.
So ultimately, what he's saying is that the sun needs to constantly sort of ventilate itself because it has this buildup of pressure between these lattice layers. So it constantly, well, not really explodes, but I mean, produces CMEs and stuff.
Yeah, yeah, and it's, you know, it's an argument that's going to continue to go on because ultimately we don't know if it's chemical reactions just on the surface that are sort of driving the activity, or if it's sort of this intercalate activity, or if it's something going on in the poles contributing to that too. I mean, I would suspect there's probably something going on at the poles because we have these enduring coronal holes there. So that's an interesting thing.
Well, again, that's not entirely correct because at the maximum, coronal holes migrate towards the equator.
That's not correct either. We're just going to have to disagree on this.
Well,
we've argued about this a couple times.
It's your problem because that's what we're doing. I can actually give you a link to the model, perhaps. Let me see. But whatever.
So this is
one thing.
This is what the sun would look like from the pole.
Let me see. Well, I don't know. Like, we haven't seen the sun from the pole, and again, you have to clarify like which wavelength is it, etc. Like, if it's visible light, then probably not, because the sun would be just white.
Yeah, no, it's that's 171 angstroms, actually.
Oh, I actually, I think I know how they made it, but yeah, I would say that, yeah, probably.
Yeah, it's a series of images from I think it's, which one was that? The Ulysses, the one that flew really high.
I don't think Ulysses had any cameras. I think it's one of the like solar observing satellites, such as SDO, but it's not SDO, but it's something similar to that. And you just combine the images of the opposite sides of the sun in this particular projection.
Yeah, and
so you just map the lower, let's say, hemisphere.
I see what you're saying.
On one day, and 2 weeks later, you also take such an image and you project them onto such a thing. And that's why you see this discontinuity, like this horizontal line.
But just to clarify for the viewers, I don't know what Eugene's talking about when he says that the coronal holes migrate to the equator at solar maximum.
Well, they do.
I'm at a loss.
That's how solar pole flip happens.
They don't entirely migrate. They're some coronal.
No, they do entirely migrate, because every next cycle you have the reverse polarity, which means that the coronal hole with one magnetic field direction have gone to the opposite hemisphere. How otherwise could it happen?
I don't know. I'm not gonna make an argument about an observation that I don't think exists.
Okay. I'll just gonna show you this right away.
So in any case,
that might take some time, but
yeah, we should save it for a later video.
No,
anyway,
don't do it right now.
I've got Deneb on the screen right now.
Okay.
And this is just because, what would be the implications, you think, if Robitaille's theory is correct and stars are made of metallic hydrogen? How does that figure into the rest of cosmology?
Well, there's actually a pretty serious implications because
Yeah, I'd say.
you have to reevaluate everything that you think you know or you think you knew about the stellar evolution, like
Exactly.
stellar populations, like how the elements are produced, like again, Big Bang might actually suffer huge losses here because again we have a huge number of assumptions of population one stars, population two stars, like which kinds of elements you should have in older galaxies, let's say, versus newer galaxies.
Exactly.
So all of that should have to be revised, I would say.
Yeah. And this is something I've been talking about for a long time on the channel because, in my opinion, astrophysics and cosmology are in the process of being rewritten, and that's part of the reason why Eugene and I are talking in the first place. So I've just got a Hubble deep field image on the screen here showing you quite an array of vastly different galaxies here. And I'm sure this is a pretty famous one. I'm not exactly sure which galaxies or what part of the sky this is, but this is one of the early ones, I think, from around the mid-90s when people were sort of
I've
really...
produced an animation for you of the coronal holes, and that's the year 2012, so that's roughly solar maximum, even though it had two peaks. If you remember, it also peaked in 2014. And now I'm going to show you. So red and yellow are different polarity coronal holes. So this is what you observe at the solar maximum. You see how they've migrated towards the equator and they stopped at the opposite places. And now I'm going to show you the year, let's say 19, where we had a deep solar minimum. And you'll see that coronal holes are just at the poles.
So this is coronal hole field plots with coronal holes shown via their polarity in red and green, right?
Yes. I'm not sure which one is the north and which one is the south, unfortunately.
Well, but I still see coronal holes at the poles because
well,
more of the polarity is in these locations.
They're kind of stretched, but
they never fully leave the poles, Eugene. That's the point I'm making.
How are they getting to the opposite poles then? Like, again, just compare. Okay, I'll show you this solar minimum, like this 2019, the latest picture I've sent to you, and then look at. I'm going to show you the previous solar minimum, which was 2009, let's say. So.
All right, and for your viewers, here's this one.
Yeah, so you see one hole is at one pole and the other is at the other, right? So everything is kind of cool. But this is solar minimum situation. Right?
The reason I'm having trouble looking at this is because I never look at this particular data set, and it just looks really weird to me. That's all.
I'll send you the link. You can produce these movies.
Oh, I know. I view the Gong 2 data on the regular.
Okay.
I know how to bring this data up.
Mm-hmm.
I just don't look at this particular slide. I only look at the top view ecliptic plane field plot and the line of sight field plot.
So this is 2019 that you're looking at, and now open 2009 from the previous minimum. The next link that I've sent to you.
That one?
No, that was the very first one.
Oh, hold on.
There's the latest message from me.
Oh, okay.
2009. So you see, they switched places. Like in 2009, the green is at the bottom and the red is at the top. But in 2019, they have switched places. So
yeah,
can you tell me how can this happen if they don't migrate towards the equator and don't continue moving further?
It's a hole, Eugene. How does a hole move? You're talking about the material surrounding the hole moving, not a hole. A hole is a lack of material.
Well, it's just I don't know.
I know.
How you say it. Sophistics.
You're talking about the polarity, but yeah, the point is we don't know how it works. That's why. That's why we're arguing about it, and that's why it's an argument worth having. So thanks for having said argument.
Well, I think I understand how it works. I don't really know what internal processes drive this motion, but on a like a superficial, descriptive, let's say, level, I think it's pretty clear. Like coronal holes sit at the poles at the minimum, then towards the maximum, they start like extending towards the equator and like slowly creeping there. At the maximum, they're at the equator at the opposite sides of the sun, and they continue moving so that at the next minimum, they're at the opposite poles with respect to the previous minimum.
Okay.
That's basically how I see it.
I totally understand. Now, I've got a question for you, just kind of out of the blue that just sort of came to me when you were talking there. Do you think that solar minima or solar maximum is more likely to be associated with noval events?
I have no idea because, again, we have no theory, let's say, of how such events occur. And we don't even know if the sun, like this type of star, can nova, regardless of what some people think. Like, I don't think there is enough evidence to claim that the sun can nova at all.
I think a lot of the chemical stuff, the chemicals from space. I think there might be a higher ability for the sun to create elements that we don't expect it to create, perhaps in its atmosphere. Who knows? Who knows what the dust is like? That
It's
the
actually
solar
one of the
system.
arguments that Robitaille makes that the sun is not only producing elements in the core, but the fusion actually occurs even in the uppermost layers of the sun. So basically anywhere where there is this lattice, even though Robitaille actually claims that in the core there is a different type of lattice, by the way, we didn't mention that.
Yeah,
He
I mean,
claims there's a, like, I think it's called body-centered, like basically cube-like lattice, I think at least.
yeah,
I may be wrong.
I
I've
think
read
so.
these papers like 5 years ago, so don't quote me on this. But I think he claims there is a cube-like lattice because one of the reasons is that the internal layers of the sun, like the core, it actually rotates like a solid
Like
body.
a solid body, right?
So it should be a different phase anyway.
Yeah. Yeah. So, yeah, I guess that sort of covers it. That should muddy the waters up for everybody for a month if they want to sort of delve into all this stuff. But definitely, everybody should certainly read, uh, you know, the Sun on Trial 40 Proofs Supporting a Condensed Matter Liquid Metallic Hydrogen as a Solar Building Block.
Well, I mean, not many people are used to read scientific papers, so there's plenty of video materials with Robitaille, both on, let's say, conferences, like you just search for his name, and on his own channel, Sky Scholar. So you can find it all there.
Exactly. The YouTube channel Sky Scholar is absolutely fantastic. Maybe not as good as Eugene the Philosopher, but it's pretty good. So make sure you subscribe to both of those. And we're showing Eugene the Philosopher. Congrats on 230 subs, man. Fantastic. Fantastic.
I actually had 235 like a few days ago. Maybe 5 people unsubscribed. I don't know.
Well, anyway. Yeah, so also Eugene may be familiar with Electric View. I know we've... Have we? I don't think we've ever been on an Electric View call together, have we? Anyway, whatever kind of view you have, it better damn well be electric. Otherwise, it's not going to be the view.
I was one of the basically founders, so to speak, of the Electric View. Not the, like, among the chosen few, but among the larger part of the crew. And we've had pretty cool discussions, like 2 years ago, and but I quit in like March, I think, of 2019 because of, again, some issues with the production pipeline. Let's call it that.
Oh, okay. Well, yeah. Anyway, so yeah, anything else to add about condensed matter and what if celestial bodies were made out of it? It's a bit of a rough topic to be covering, but hey, you gotta push the boundaries. Otherwise, who's gonna do it?
Well, I'm basically, my default position is to be as skeptical as possible. So, and skeptical means like I do not make any judgments before enough data is available. And there is no data available about the internal structure, let's say, of the sun or Earth. So I don't make any judgments about those. Like, I'm open to different theories.
Sure, sure. So, all right. So thanks, Eugene. Thanks, viewers, for tuning in. Don't forget to press like and subscribe on our YouTube channel also. We put up a long one yesterday, 21-minute video with only close-ups of the sun, so the ones that we show on the daily space weather videos, Eugene. You might want to check that out. It's pretty sweet. You know, watch it on a big high-res screen if you can. And also we did a 2-minute video about just sunspot 2782, the new one just rising on the southeastern limb now. And yeah, that's about it. So thanks again, Eugene. Hopefully you'll join us again for another The Diamond Anvil Too Hard to Smash. And yeah, anything else to add, Eugene?
No, I don't think so. It was a pretty interesting discussion. So thank you, Daniel, for inviting me. And thanks to all the listeners for paying attention, hopefully.
All right, see you next time. Don't be a stranger, and don't refrain from being stranger. Eugene, the philosopher Bagashov.
Goodbye.
See ya.